Hi, this is the second video of the series of video that I'm going to explain about quantum computing. In this video, I'm going to talk about entanglement and measurement. What is the entanglement? The easiest way to define quantum entanglement is the following sentence. A quantum state is entangled if it is not a tensor product of qubits. Let's look at an example. The following example is not entangled. It's a linear combination of two cats, cat 00 and cat 01. And you can write that as a tensor product of qubit 1 state and qubit 0 state. The state of qubit 1, which is on the left, is cat 0, and the quantum state of qubit 0 is on the right of the tensor products, which is the linear combination of cat 0 and cat 1. Since you can write a tensor product between two quantum states stored independently, you can say this is not entangled. Let's look at another example, which is actually an entangled state. You are looking at quantum state, which is linear combination of cat 00 and cat 11. Since you cannot write the tensor product of two quantum states to make this quantum state, it means that two qubits are entangled. So what is the significance of the entanglement? We have to talk about the measurement first. What is a measurement? A qubit is observed by a measurement. It's impossible to see exact quantum state of a qubit, but we can get some information about the qubit state by measurement. So let's suppose that we have quantum state cat psi, which is a linear combination of cat 0 and cat 1 with two coefficients, alpha and beta. And as we said before, these two coefficients are complex numbers. And let's suppose that there is one more condition, that the sizes of these two coefficients are add up to 1. So here's the most important theorem in quantum computing, which is called Born's rule. So first one is that you can only observe 1 or 0 after measuring this quantum state. And the second rule is that the probability of observing either 1 or 0 is the following. The probability of observing 0 is the same as the size square of the coefficient of cat 0, and the probability of observing 1 is the same as the size square of the coefficient of cat 1. The third rule is that once the qubit is measured, the qubit collapses to its observed state. What does that mean? Suppose you observed 0 after measuring this cat psi. Then, as soon as you measured, the quantum state loses all its information and immediately collapses to the cat 0 state. So let's look at an example. This is a 3-qubit state, partially entangled. The label of qubits are read from right to left. So qubit 0 and qubit 1 are entangled, but qubit 2 is not entangled with qubit 0 and 1 because you can write the tensor product between qubit 2 and qubit 01. So here are what happens when you measure this qubit state. So when you measure qubit 2, you can always observe 0 because that is the quantum state of qubit 2. However, when qubit 1 is measured, you can observe 1 or 0 with 50% chances because the coefficient, which is 1 over square root of 2, has the size square equals to 1 over 2, which means it's 50%. So let's think about another situation. You measured qubit 1 and let's say you observed 1. So that means these three quantum state will immediately collapses to 0, 1, 1 cat state. So even though you measured only the qubit 1, the other qubit states are fixed according to the entanglement of the quantum state. That is the significance of the quantum state, and this principle will be the core of all the quantum algorithms and quantum supremacy. So in this video, we walk through the simple examples of quantum entanglement, and in the next video, we're going to talk about quantum gates. Thank you.